So right now I'd like to introduce Mr. Brian Gardner from True Circuits.
All right, all right, all right. All right, I'm here to, I'm going to spend most of the time talking about a new PLL, a new architecture that we just released. I'm going to tell you a lot of good things about that, how it does things that have never been possible before, and it's going to allow you to build things that you couldn't dream about. And first, I want to introduce the company, if this works. We are a leading and one of the oldest IP firms in the Valley. We've been building mixed signal timing IP for 17 years, which is 2 lifetimes in this industry, maybe 3 lifetimes in some of the other industry. See, it does happen to everybody. I haven't done a thing right. John did this presentation last time, and that thing didn't work. We're in Los Altos. We're not only very smart analog designers, but a lot of what our efforts are devoted to is CAD. So we design mixed signal IP in a way that most people don't. It looks a lot like soft IP. It allows us to do things that are very configurable. It allows us to basically put our simulation environment and our design environment and the configuration space all into one basic program. And so what that allows us to do is build a complete portfolio across about any node you can imagine. And it also means when you order, let's say, a PLL from us, you don't have to worry about what metal stack, what oxide thickness, whatever you got, we can finish the design off in an automated way at the end. You don't have to worry about that. If for some reason, we decided to use 40 nanometer instead of 28 nanometer, we've got the same PLL at that same node. And that just makes it a little easier. It's already hard to build a chip. When you buy IP, you get all the IP figured out, and then you decide to make a slight change in the process or the metal stack, and then suddenly 2 of the IP suppliers say, sorry, we don't have anything there. So that's what we do. That allows us to build products. So in a complete portfolio of IP across the whole spectrum of processes. So what we sell today is mostly PLLs, timing devices. We have various different kinds, sort of a basic clock generator that allows for very high multiplication, allows you to build very precise frequencies, and basically you can use that for about any PLL application on the chip. We also have a spread spectrum PLL that allows you to spread the energy that would be emitted into the RF across a larger range, so that way you could pass your FCC testing a lot easier. We do a little bit smaller and lower power general purpose PLL. It has a few less features, but it's about half the size and about half the power. So our idea is basically, there was a time when you designed a PLL for every particular application. That's just the way people did things. As you begin to coalesce a lot of functions onto one chip, you might need 2, 3, 4, 5 PLLs. You don't want to have 5 specially designed PLLs custom. You want to use one and program it. That way you can instantiate it 1 time, 2 times, 10 times, program it differently. You can do everything on the chip. So basically it takes a problem that was hard and makes it fairly easy. We do a DLL, which is a little bit different piece of IP derived from the similar architecture. It was very popular component of a DDR5 at DDR3 and DDR2 when speeds were slower. And we sold DLLs into practically every chip you can imagine. It's become a lot harder, and so we moved up the food chain and built our own DDR5. So now we've incorporated a DLL and PLL and multi-phase DLL. A whole bunch of our timing portfolio is now in that PHY. We can provide that PHY as a single hard macro. We've built it in a way that makes it very easy to close timing to the memory controller, which is a big problem. It has a lot of really cool features, so it does automatic. It looks a little bit more like a SerDes than it does a DDR5. Every pin adjusts individually to actually each phase of the data. So the whole idea is that it's easier to use. It has remarkable physical flexibility because of several things that we've designed in, which are different. And the idea is by allowing you to have a wide physical space, you can reduce the cost of your package, and you can reduce the cost of the board. So we want this IP to translate into a reduced bill of material. And so that's what's important there. If you want to learn more, our booth is there with the kite at the top, and we can talk more about DDR. But for this presentation, I want to focus into the new PLL. First, it goes multiple times. Now I won't listen to you anymore. It's like, is that the first slide? Yeah, that's it. Cool. The device doesn't love you, John. See, oh, now it loves you too much. It can't make up its mind. First it's flirting, and then it won't even talk. Sounds like one of my daughters. Okay, so state-of-the-art architecture. I mean, we're one of the leaders in PLLs. John's the president of our company right there and our #1 slide turner. And he built some of the seminal architectures in PLLs, and this is the next one. What's great about this, really low jitter, but also can multiply a reference clock up to 250,000. Think about that. Most people multiply by 2 or 3 or 4. Even 8's a big number. 250,000. I mean, that means you can do things like you could have a 32 kilohertz crystal, a 32 kilohertz reference clock, crystal, really cheap, really small, really robust environment, and you could build a gig or a 2 gig or a 3 gig output frequency. So that allows you to do things that couldn't be done before. It allows you to maybe save some cost of bill of material, like we talked about in the DDR5. It also means you could conceivably drop to a really low frequency easily. You got a 32 kilohertz clock. Maybe you just want to turn off everything and run a heartbeat at 32 kilohertz. So what we want to do is not only solve the PLL problem, now you got one PLL you can use all across the chip. If you got a really low jitter requirement for a SerDes reference clock or an analog front end, you're covered. And you can also use it for some place where you just want to have a really low reference clock. But again, what we're trying to do with the IP in DDR and the IP in the PLL is offer new opportunities. Not just fill the IP need that you have, but allow your architects or your business people to dream about something new. You know, a different package, something much lower cost. So, you know, dream on with us. This PLL also provides, 26 bits of accuracy. So from this low frequency, you can produce a very exact frequency, which is important in some applications, right? Some places you're doing some kind of audio, or maybe you're doing a pixel clock, and you need 157.25, and you can get all of that. And then it also has spread spectrum that can be programmed in. So again, now you have something that's, a little bit of a Swiss Army knife. You can do whatever you need to with it. You don't have to buy a lot of different PLLs. You can program it for whatever you want. Again, it's a brand new architecture. It's a very high-speed digital architecture, very clever, that allows you to have that range and still have the really low jitter that we're talking about. So it'll be available in all the processes. So again, because of the automation we talked about, it's easy for us to port to different processes. One of the other things we do is we even have IP that's brand new IP that can be ported back to the old process. And that's very different. Most of the firms, especially the bigger firms, they come out with a new IP, it's at 28 and only later. It's at 16 and only later, right? So they're only worried about the front end. That's where they're going to capture all the revenue. That's where they're going to get your ROI. But there's still a lot of people building chips at 28 and even 40. And as this IoT thing begins to take shape, you're not going to You're not going to put a wearable in 16 or 28. You might put a wearable in 55 or 90. It's not cost effective. You don't need to put a billion transistors on there, but you might need a PLL. In fact, you might need a PLL that can run at a really low frequency and then be able to jump to a high frequency just for a few seconds to send information or data analytics or whatever we're going to do with all this IoT stuff. Phone home, Trojan virus, phone home, bring in whatever it needs. So that's another thing that's different. Us having a portfolio across the whole process space and being committed to the older nodes where there's still a lot of people doing good stuff. I believe that's it. I have no idea what our time is. We're a little ahead. So any questions, or should I go deeper somewhere? John's going to ask me a question. Less than 500 femtoseconds integrated from a megahertz all the way up through Nyquist. Extremely low. Even with a 32 kilohertz clock, the designer says, and he goes, yes, but then he begins to move a little bit. So the answer is yes. Yeah. Obviously, the jitter specifications have moved from something that's just a point in time to something that's integrated across the space that makes any difference. But this allows us to meet even the tightest jitter requirements for any SerDes reference clock. What's that? No, you don't need to trim it. It doesn't need to be trimmed at all. The PLL does. But let's dream a little bit again. Let's say maybe you want to run off a 32 kilohertz resonator, something that has a little bit of PVT variability to it. But let's say for whatever reason it's cheaper, or maybe you're building some kind of IoT device where you already have MEMS technology that you're paying for. Maybe you want to put it on there too. If you did need to trim it, because we have very, very precise frequency, you could, if your reference clock were to vary and you wanted to trim it over temperature or voltage, you could do that. So again, it could be something that you could use to build something that doesn't exist, or crush your competitor in a way that they could never see coming. But for us, if the reference clock is stable, the output clock's going to be stable. There's nothing that needs to be done. No trimming. That would be not very much fun. Other questions, comments? Should I go back and spend time on anything else, like maybe DDR? Should we do a comedy act? You're good at that. Yeah. I could maybe be the straight man. That's supposed to be the hardest thing.
It is. That's Dean Martin.
So, Brian, I have another question for you. What kind of DDR standards can you support with this DDR interface?
You already have a straight man. I like it, Dean Martin. You can have a martini next time. I could do that. I think I could do that. 4 o'clock, that'd be close enough to happy hour, too. So we cover DDR3. Right now we cover DDR3 and 4, LPDDR2 and 3. And we're in the process of adding LPDDR4. So they'll all be combo. You can do both, multiple protocols with the same piece of silicon, which is interesting. Some of the other things on DDR is we've added a bunch of features that are basically instrumentation. So we do things because I told you we track all the read timing. So as the read timing changes over time or PVT, we're constantly adjusting. We actually put a strobe separately for every pin and separately for the even and odd cycles. So we also, if you know much about DDR, if you don't, fall asleep, there's a read DQ that comes back, and it can change quite a bit over process and temperature, or temperature and voltage. We track that too. So because we track it, we can also provide ways where you can look at it in more detail. You can look at the jitter. So you could basically go on with a little bit of firmware and a laptop connected to your DDR controller, and you could get the jitter of the DQ, of the switch point. You could get the jitter of the DQS. You could basically plot the entire data eye. We also have a feature, sort of a poor man's TDR, where you can measure flight times. You can launch a signal and figure out when that signal it bounces back. You can tell how long the flight times are. You could even possibly measure reflections due to large impedance mismatches. So we built a lot of things. We also added some functionality to do automatic write training and automatic VREF training. So the idea there is to do as many things automatic as possible. That way you're constantly tuning, you're constantly adjusting things. And also it means you don't have to write drivers. So a lot of the training and tuning that has to be done in DDR, some poor guy at chip company X has to spend 6 months writing these drivers, to tune this stuff. And it's cumbersome work. It's the kind of work you don't get a lot of credit for. It's like, wow, that should have only taken a week, and it's not. It's actually really hard. Not only is there a lot of software to be built, you have to figure out the algorithms. You have to talk to your board guys. We're doing all that automatically. So as you go around here, most chip companies will say, no matter how expensive 16 nanometer is, I'm still spending more money on software than hardware. So for us, anywhere we're in the ecosystem, if we can help them like less software, then that's good. We're going to reduce their cost to bring a chip out. And a lot of people don't think about that. If you're a hardware guy, especially if you're a mixed signal guy, it's like, so what? Somebody's got to write some software. What are they whining for? They don't have a hard job like us. They don't have to worry about transistors. But all that adds up. If every single piece of IP needs a few weeks of work that some guy has got to write a driver for, now you're talking about 75 pieces of IP. You're talking about a couple of years of work. It's drudgery. And also, it's the kind of thing that goes wrong, chip dies, right? I mean, if you can't tune your DDR and your chip can no longer talk to its memory, it's dead. It's not going to do anything. It's going to go back to the shop. And, that's a big deal. Yep. Are we in FPGAs? Yeah, we have PLLs that we provide to FPGA vendors. So, we're an internal supplier. In some cases, those relationships are public, and in some cases, they're not. It's interesting too, because to build something in an FPGA, it's got to be really, 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 really configurable, because there's just so many different ways. So when we put a piece of timing IP into an FPGA, it usually requires quite a bit of extra work on our part to make it do so many different things. And I have to think about the one I'm thinking of is public or not. I'd have to think about it a little bit more. Moss? Yeah. Exactly. The biggest thing are people that do SoCs. Although, over a wide range. I mean, I sell a lot of 130 nanometer PLLs to people that are doing, interesting things, really. 1.5 gig? What's the maximum output at 130? 4 gig? It's pretty high. If you go to our website and you look at the product portfolio, I mean, it's right in front of it, scrolls on and on and on and on. But probably faster than about anybody would do anything at 130. Yeah, it's faster than probably unless you're doing something really special. But the other thing is, if you run fast and divide down, you get some advantages in the jitter. Exactly. So, in some cases, they would use the frequency overhead for that. Are we near the end? Where's my martini?